is I get better and better at doing this a smooth, short derivation every year. So we have to get the formula. So there's a formula on your equation sheet that says elastic collisions next to it. And it's got V1, V2 with a bunch of minus signs. How on earth did I get that? Well, I did physics. Watch. No, really. Um, when a collision is elastic, what does that mean? We just learned last year. Okay, momentum's always conserved. Elastic is a special kind. So in honors physics, good, good, good. In honors physics, momentum is always conserved because it's always conserved in the universe. There's one exception where you have an outside force like friction acting on your system, but I think that's cheating because you're just failing to include whatever's exerting that force in your system. If we just wrapped the system around whatever that thing is, even if it's planet Earth, then we would conserve momentum permanently. And we find that the universe does. But that means, okay, kinetic energy. So I have to have my total initial kinetic energy equal to the total final kinetic energy. So if I have two carts, two things, they can be M1 and M2. Yes, and I'm going to end up with just V1 and V2. So I have V1 initial, write this down squared, plus 1 half MV M2, V2 initial squared equals, oh my word, 1. Well, I know one thing we can cancel at least. We can get rid of those 1 halves. V2 final squared. Holy smokes. Okay, we have 4 different velocities. We could assume we know 2. We usually measure them to start. What are we going to do? Okay, well, like everyone's too eager to blurt out, we conserve momentum. So we also note that we have M1 V1 initial plus M2 V2. Now these have to be vectors. They have to have plus and minus appropriately. Because if you just add them absolutely, that's totally not true. Right? It matters if they're pointed against each other and have opposite directed momenta, or if they're the same direction. We have V1 final plus M2 V2 final. Where did the square go? Did I forget one? Nope. This is momentum. So the blue is kinetic energy conserved on the top, and the green is momentum conserved on the bottom. So both those things must be true. Oh no. That's right. So I have to be a real physicist for once, and not just play around. We are going to make, let's see, well, we can cancel out all those halves, because everything in that equation is a half. So that's just silliness. We really only need our half when we do work and energy. But okay. I'm going to collect the m's. I'll show you what I mean. First, that means I want M1 on the left side and M2 on the right side. Because maybe, just maybe, I can actually get rid of m's also. Okay, so I take my kinetic energy equation, and we'll keep it blue to color code. Okay, so I have M1. I'm going to simplify my steps. Okay, so I have V1 squared minus V1 initial squared minus V1 final squared, because I've subtracted my final term over there. This is too long to show all the algebra steps. I have to be a grown-up physicist and skip some steps, visually at least. If you've got you can write small with your pencil, you got lots of space in your notebook, you could check if I'm doing the steps right. Okay, and then I group the same thing with M2, and here to not confuse you too much, this is V2 final squared minus V1, no, minus V2 initial squared, because I subtracted my V2 term over to that side. Huh, now they look pretty nice and similar, except I have this minus sign in between. I'm not going to do it this step, but if I multiplied, I could factor out a minus 1. I could put the minus out here, and then those terms would flip around. I'm probably going to have to do that in the future. Okay, but let's do that to the momentum equation too and see what happens. So I do my M1 term. So I have mass 1 times V1 initial, whoops, minus V1 final. Looks okay. And over here I've got M2. Oh, that does look okay. V2 final minus V2 initial. So I collected my mass terms, M1 on the left side, M2 on the right side, and then I factored them out of each side. I'm actually almost done. Man, I'm good at this. Do you see what to do? I'll let you keep writing. That's fine. Sure, Paul.
Why is it on the left side initial minus final and the right side is final minus?
Oh, that's just how it worked out. If I wanted if I wanted initial minus final on the right side, I could like factor out a -1 just to write it the other way. But I don't see quite any reason to do that at this time. Right, so I had to subtract the initial from the left side over to the right. So that's why initial is negative on the right. And I had to get to move, I'm collecting terms by which mass they apply to. So on all the mass 1s on the left side, and that means I had to subtract M1 final from both sides, and then it became negative on the left. Speaking of both sides of equations, all your career in math, you've been taking terms and adding to both sides or subtracting both sides to move things around and solve it down to whatever you're solving for, right? Yes, Ryan?
Just for the next step, right? Can I say what I
Sure.
should do? Well, first, I think instead of taking the negative out from the M2 side, we should only take it out from the M1 side, so you have the final
Final
minus
minus initial
initial.
would be better.
And then you can do M1 over M2 is equal to, and then
Yeah,
set both of
that's
those.
pretty good. But I actually want to get rid of those M1s and M2s.
Yeah, yeah, you just
So,
set M1 over M2, just take the V quantity and set it over the other V quantity, and then you put M1 over M2 on both of them, and then you set it equal.
oh man, I have a simpler, sneakier way to do it than that. It's even sneakier. So, okay. So, I teach this in Algebra 1, and I can barely contain myself. And they're like, man, this guy's crazy. What is he even on about? Uh, so, when you divide or you subtract things from both sides, you divide or multiply to both sides of the equation, why can't you multiply the equation by a whole equation? As long as you're doing the equal things to equal sides, then it stays equal. Why couldn't you divide an equation by an entire equation? I mean, what insanity is that? Who would ever do that? Well, we want to do that. And an equation can be x equals 5. It can be x equals m1. It can be m1 over m2 equals some stuff. It can be anything we want. Why not just make this a fraction? Divide the blue one by the green one on each side, and they're equal sides. So yeah, I'm totally allowed to do that. I divide the blue one by the green one and just cancel my M1s and cancel my M2s simultaneously. Oh, it's so great. But oh no, what happened to this? Wait a minute. Now I have final minus initial, initial minus final. Craziness everywhere. Nope. That's why, and this is why I haven't done it quite yet. How can I divide this squared thing by another thing? Don't I have to do crazy long division?
They factor out to the initial minus V1 final.
Yeah, if you really paid attention in Algebra 1 class, those top guys are the difference of squares. Remember that? So on the top, I don't just have v1 squared minus v1 final squared. I have v1 final plus v1 initial plus v1 final, and I have v1 initial minus v1 final. I didn't quite want to mess with the negative signs yet because of that. See how they're written in the same order? And so you'll definitely have 2 minus 1. It's tricky. If I played with the negatives, I might lose one somewhere. Don't trust myself. Maybe you're amazing mathematicians, you could do it. Okay, so I do my division, and I get v1 initial plus v1 final equals v2. It could be, it's plus v2 final plus v2 initial. Can't say words. But now they're just added on both sides, and I can do initial plus final, and final plus initial. Okay? And that's what I had to memorize as a freshman physics major in college, because I couldn't redo all of that even as a freshman in college fast enough. So I had to do initial plus final for number 1 and initial plus final for number 2. They're equal. Now, you can observe this effect in reality, and it looks a little different. They like to rearrange it. Okay, so what appears on your equation sheet. Okay, but all I did was insist that kinetic energy is conserved. We wrote it down. Momentum's conserved, and they're both conserved at the same time. So we combine their formulas. Okay, on the equation sheet, I want to have the initials together. So I have to write v1 initial minus v2 initial. Okay. And I really like that 1 minus 2. And now that I'm at my final simple answer, I'm going to rearrange it. So to get minus 2 minus v2 final over here, I'm going to need a minus like that. Why would I do that? Because then when I subtract v1 final over here, v1 final goes right there with its negative. And so that's what's on your equation sheet. But if you prefer to add the initial velocities and the final velocities together, that also works. And so here's what's happening. In physical reality, you notice even if they had different masses, okay, I canceled the mass out. Doesn't matter if one's more massive than the other. Doesn't matter what everything else is. It matters you have 2 different velocities, so they must hit because they have different speeds, and then they conserve kinetic energy. What's happening is if I get one of these guys going slow and I catch one up, at first they're approaching at some speed. I'm going to try to do it slow so you can see with these physics cards. And then after the collision, they're moving away at the same speed. The relative velocities, the collapsing velocity, the difference in velocity before equals minus the velocity after. They're moving towards each other before and then away. That's what the negative sign is, and then they're moving away after. And if kinetic energy is really conserved, then those relative velocities have to be the same but opposite. They're just going away instead of towards. See when they're moving at each other. Okay, we'll try it from here. Well, see, the other one doesn't stop when it's elastic. Okay. These are equal, so they trade velocity. That's another kind of quirk. But let's see. So we're going slow. Oh, it's good. It goes really slow. Man. You would think if that was stopped, then I would just bounce off. But if they're both moving first, then I don't stop. Continue slowly. Okay. The relative velocity is the same.